Okay, YouTube, in this video we're going to be exploring what we call logistic growth models. And so we've looked at exponential growth and decay. This is kind of like a shoot off of exponential growth in which we have something like, I guess if we read through this first sentence here, it's a really good explanation. From population to growth to the spread of an epidemic, we say nothing on earth can grow exponentially indefinitely. So when we have situations that grow exponentially, you can kind of see on this graph over here, so it starts exponentially growing here. There's a point at which, let's say in terms of spread of disease here, your earth has only so much population to infect, and so there's got to be a point at which people are still really getting infected really quickly, but because the decrease in population, people are dying, and you only have so many people, maybe, then you have less people to infect over time. And so there's this like limit. We see that it has this horizontal asymptote, which provides a limit at which we cannot infect more than, say, in an infection example. So we would say from population growth to the spread of an epidemic, nothing on earth can grow exponentially indefinitely. So by mentioning that, again, here we say growth is always limited. And we say that this is shown in this graph that we took a look at on the right by this horizontal asymptote. So we say that the logistic growth model is a function used to model situations of this type. So here's what I can tell you about logistic growth models, and I think the fabulous thing about them. For the most part, we say that, looking at the models here, these are things where we see that there are a lot of, I guess, letters. We say A, B, T, E, C, all of this going on, and a lot to remember. But basically, here's what I want everybody to know. A, B, and C are constants, and C and B are positive because, of course, we don't want to have negative, well, I guess we say it is given that C is positive, and B, we want to be positive here no matter what. So given this mathematical model, what I can tell you is the splendid thing is it's usually given to you with all of these values known. So that being said, what we're going to do is look at kind of playing around with logistic growth model here and kind of what it looks like in terms of evaluating it. So we say in a learning theory project, psychologists discovered that f of t equaling 8/10 divided by 1 plus e to the negative 0.2 t is a model for describing the proportion of correct responses, f of t, after t learning trials. So we're going to label a few things here. We're going to start by labeling what f of t represents, which is the proportion of correct responses. So we say the proportion of correct responses on this assessment. And then we'd say t is the number of learning trials. And so it's important that we recognize this here, number of learning trials. And so we see that if we were to see that our number of trials continues to get bigger and bigger, one might surmise that the proportion of values, if we were going to say that it's at least shaped like a logistic curve, it's going to look something like this, and there's going to be some limit at which, no matter how many learning trials you have, you're not going to, get better than some score or something like that. Proportion of number correctly answered. So we say find the proportion of correct responses prior to learning trials taking place. So basically what we're saying is, with respect to this situation, we're saying before we do any learning trials, when we say t equals 0, we're going to say no learning trials. This would be before any learning trials take place, and we'd say that's our initial amount there. So really what we're going to say for part A here is this. We're going to say f of 0, and what we end up with is this 0.8 over 1 plus e to the negative 0.2 times 0. And so essentially on the bottom here, let's see what we get here. We get 0.8, and we get 1 plus e to the 0. And really that's just a 2, I would think. So we'd say 0.8 over a 2 really gets us 0.4. And so we could answer this question, before any learning trials take place, we say then 0.4 is the proportion of correct responses. So I'm going to write that down in this particular instance here is at time 0, then we knew that this was the proportion of correct responses. So for part B here, it says find the proportion of correct responses. So again, find the proportion of correct responses means solve for y, but we say when there are 10 learning trials. So they've given us a t value here. We say t is 10. We're going to go substitute this in for t and solve for what we want here. So I'm going to transport b down kind of in this area here. We say f of 10. This would be the same kind of idea, except for this time we have 10 learning trials. So 1 plus e to the negative 0.2 times 10. And so we really get 0.8 all over 1 plus e to the negative 2 power. And so we'll get an approximate value on this one here. But let's go ahead and do that. We say 0.8. And we're going to divide by all in parentheses, 1 plus now e to the negative 2. So we say e, we have to hit second ln, and we say the negative 2 power. We're going to end that parenthesis and also end the denominator parentheses. And we get this, we get about 0.7046. So 0.7046. This would be the proportion of correct responses. So after 10 learning trials there, we would see that the proportion would be about 70%, a little bit north of that. So the last part here, it says, what is the limiting size of f of t? So go find f of t, but we say, what is the limiting size of f of t? The proportion of correct responses, but as continued learning trials take place. And so basically what they're saying is t gets very large. As t goes to infinity, what are our proportion approaching? So what I did was I graphed this in Desmos, and you can see that I've got this up over here, and it kind of doesn't look very interesting right now. As I say, the proportion would have to be between 0 and 1. What we could do is we could change our y-axis to go from, let's say, negative 0.5. We'll go just below the x-axis there, and we'll go up to, how about a little past 100%, 1.50. And so we'd say, looking in this neighborhood here, you could see that it starts off at time 0. We could see that the y-intercept there was indeed 40% correct, but what we want to ask is, as time's getting bigger and bigger, what's the proportion of correct responses approaching? We see that's the y values there. So if I scroll to the right here, what we're ending up seeing is that the proportion of correct responses out to the right here is getting really, really, really close to, I'd say, about 80%. And so as I go to the right, finally it should click over. I'll bet you it does. Finally, one more time. There it is, 0.8. And so we can't say it's well, I guess the limit would be 0.8. We're not doing calculus here. But we would say that to answer part C, we would say as t approaches infinity, we'd say f of t is approaching about 0.8 is what we want to look for here. Cheers.